So this just continues from the last one where we're looking at, electromagnetism, focusing here on forces on moving charges, right? So last we were kind of looking at the magnetic field created by moving charges. Um, and that's sort of this first little sentence I have here. Moving charges produce magnetic fields, which we just saw the last lesson, but also magnetic fields affect moving charges, right? So it works both ways, and fundamentally that's because really this is like one united force, right? This is really just electricity. Um, so so let's look at one of these right here. Let's look at this, if I can make this a little bit bigger, right? We want to know, so we've got this magnetic field here represented by this big magnet. And I've got a current carrying wire. You can all look at that and see which direction the current is going. It would be coming out of the page, right? So you can use the right hand rule and you can say, okay, well, I'm going to have some magnetic field here. And if this wire is coming out, I put my right thumb sort of on the page, and that means the magnetic field would go around this way. But remember before I was saying, like, anytime you've got kind of a magnetic field, you could look at that like, okay, basically if I had a little magnet here, right, it's the direction sort of a north pole would go, right? So you could basically say, that's probably too small. I'll try to make it a little bigger so you can actually see it. Right, so you could say that would be the north and that would be the south, right? If you sort of represent this magnetic field as if there's a bar magnet there, right? You could kind of draw it that way. And on the other side, if you were to draw it here, you'd draw it the other way, right? North, south, if you wanted to do that. But let's not worry about that one. Now let's consider the magnetic field itself, right? Just from this big horseshoe magnet we've got here. Magnetic field lines always go from north to south, so we'd have magnetic field lines going like that. And really these would be all over, right? They would also go through here and they'd be kind of going around like that. We could really draw all these in. I just, for the sake of my little drawing here, I'm not going to draw all of them or leave them there. And similarly, we could represent that sort of as a little like magnet or whatever here attached to that, right? So we'd have, this would be like north and south, right? If we kind of, maybe let me move this over a bit. There. Just so it's maybe a bit clearer what's happening. So we've got two magnetic fields, and I find it might seem a bit silly sometimes drawing these magnets, but if we've got two magnetic fields, which we can draw, they're sort of magnets like that, right? We could represent them that way. What should happen if I have these two magnets like pushed against each other? Should there be any force on them? Should they try to get closer together, move farther away from each other? What should happen? Yeah, absolutely, right? They want to move apart. This is like I'm trying to push the south end to the south end and the north end to the north end. These don't want to be together at all, and so as a result, I get a force on this wire that's in that direction, right? So if I set up something like this, if I put this type of wire like this with the current coming out of the page in a magnetic field like this, I should see the wire start trying to move away from this magnetic field. And similarly, if I were to flip this magnet, right, so that the south end was up here and the north end was down here, but leave the wire exactly the same, I should see a force in the exact opposite direction, right? Because then this magnet here would be oriented the other way, and I would see an attractive force. So I'd see the wire go in. We can actually do this with two wires, right? We can say, and hopefully these arrows sort of come in here. So if we've got current in the same direction, right, we can look at what the magnetic field would be. So if you look at, well, both of these wires, it's going to be the same. So point your right thumb in the direction of the current. If I'm looking at either of them, let's look at this wire right here. Point my thumb in the direction of the current. My right hand, my fingers are coming up on the left. So that means there would be a magnetic field like this. And on the other side, it would be going down. Whoop. I don't know how many I need to draw here, but there we go. And it's going to be exactly the same for the other wire because the current is going in the same way. So what would I expect to happen if I've got, let's just look in between the wires, right? I've got a magnetic field going into the page here and coming out of the page there. So they're oriented in opposite directions. What do I expect them to be attracted to each other or repelled? Attracted, you got it. Right? And that you can just go to like sort of this example here, right? If you've got magnetic fields that are the same way, they're going to be repelled. If you switch that up, right, they're going to go the other way. And you could probably already just guess if you've got currents going in opposite direction. And just to sort of show, because I don't think these arrows come in really well. We've got current going up on the first one. That's identical to what we just had. And it's going to look like this. And for the other wire, the current's going down. You can just double check. Use your right hand. Point your thumb down just to make sure you're really good with the right hand rule. And check that you get the exact same magnetic field I do, which would be like this. And so these should repel. I hate words like that because I'm never sure if I spelled them right. Hopefully I did. And if not, hopefully you at least know what I mean. You're like, oh, we didn't know there's two P's. That's why I teach physics, not English. Just as a reminder, see, that's why I like making these notes, then I can try to remember stuff. The units of magnetic field strength, if we haven't really gone over that, is the Tesla, named after Nikola Tesla. And you can actually probably this one here would be a little bit more, right? Newton per coulomb per meter per second. And that sort of tells you all the things you sort of need to get a magnetic field, right? To get some sort of force on something, right? Is that you're going to need charge and you're going to need some velocity of like moving charges. All right, so let's just look at the force here and not like the details of it or how we get the equation. We've got a moving charge, which I've sort of tried to indicate right here. All right, this is a positive charge. Obviously, I've lost any sense of what color is supposed to represent what here, but it's got a plus sign, a little proton or something, some positively charged particle moving with a velocity that in that direction to the right, sort of on the page. And you can see the magnetic field is indicated here as coming out of the page, right? So it's perpendicular, 90 degrees. Right? So would we expect a force on this thing? Yeah, it seems a bit weird. It really is. Like, go back to like this example up here, though, right? The magnetic field here is created by moving charges, right? That's a current carrying wire really is just a bunch of moving charges. So here it's just one moving charge. So you could sort of say, well, conventional current, we consider positive charges. Right, so this moving charge you could look at as having this sort of magnetic field around it. And yeah, it should move. So in this case, right? If you looked at the magnetic field around this thing, you'd want to say, well, let's consider that just briefly for a second. We've got a magnetic field coming out. If we try to represent the magnetic field of a particle moving this way here, right, it would look like that on the top and that on the bottom, right? If we're just drawing the magnetic field as sort of going around, right, for a charge moving in that direction, right, it would be, if that was like sort of part of a wire like this, right, you would say, oh yeah, the wire would have a magnetic field that's coming out at the top and going in at the bottom. Now remember, we just said if you've effectively got the same magnetic field, right, they repel, oppositely oriented, right, opposites attract. So here at the top, it's the same as the magnetic field, right, so it's repelled. Down at the bottom, below the charge, it's opposite, right, the magnetic field is opposite the magnetic field it's in, so it's attracted, right, so both of these sort of work together. And as a result, we have a net force in the downward direction. All right, now we've got, now this is the best I can do. Like I said, a lot of this stuff is three-dimensional. So we have to do our best. You looking at a screen and me kind of right on this thing, and we got to figure out what's kind of happening here. So in this case, the magnetic field is indicated with these arrows. So it's sort of, now if you look at 3D axes, you look at this sort of black here, I did sort of what most people expect when you look at 3D axes, and this is one, you can do it this way, absolutely, right? You can have the standard XY right here, and then you can have, now when you're looking at Z here, remember, picture it kind of coming out of the page, right? So picture that sort of your third dimension, right, coming out / going into the page if it's negative. Often you'll see these axes done differently. You'll see X, and the textbook might do this, X, Y, Z. That works too. It doesn't really matter what you call them, right? What matters is that all three of them are perpendicular, and technically when you go from X to Y, it should follow the right-hand rule. So X to Y, your thumb should point in the positive Z. So either of these work, but I'll just go with this one for now. So we've got our magnetic field, and we've got this red here represents some sort of particle here. We've got some, let's say, some sort of positive charge here, and this is the direction it's sort of moving in, right? And if you can't really tell this V here that the particle's moving in, I'm going to do my best to draw this, but can you all sort of see that? So what I'm trying to show you is we've got this little charged particle, and it's moving with this speed v on the xz plane, right? So it's not moving up or down at all. It's just moving in the xz plane with these two components to its velocity. And we could actually even give you an angle for that. We could say that this this velocity has a certain angle, theta, relative to the x-axis, let's say, right? And so we want to look at, well, is there a force on this thing, right? Once again, it's going to be perpendicular. But remember, if you have magnetic fields going in the same direction, you don't really get anything, right? So technically, this component, you could look at it and say, well, there's two components to this velocity, right? There's, oh, that's a terrible color. Oh, let's just use the red. Right, you could say this is the x component, and then here you've got a y component to the velocity, right? So this one here the x component of the velocity It's parallel to the magnetic field, which remember is these sort of light orange / peach color. It's parallel to it, so it has no effect. I should write that in, right? It's parallel to the magnetic field. I'll even just call it B field because that's what we're using for magnetic field. So we have no effect. But the y, Vy, is perpendicular, right? I'll just use the perpendicular sign here. So this is the component of the velocity that is perpendicular to the magnetic field, which will result in a force. And you can do kind of that same analysis I did in the last one where you say, okay, yeah, imagine at least a component of this velocity is moving in that direction, right? So you could point your thumb in that direction, do a magnetic field, or sort of do your finger, or use your fingers of your right hand and say, on which side is it opposite to this magnetic field, right? And that would show you that there is going to be a force on this thing in the up direction. I'll try to draw this. That will result in this. Okay, assuming you all believe me about all this. But again, that really is all you need to understand. Like, there's going to be a force if you get the perpendicular component. But I wanted to say that because we have another right-hand rule, we don't want to have to actually go and do that every time and look at that in detail. Same way, even when we had a solenoid, right? We didn't want to have to actually, break it apart in that. We just wanted a different right-hand rule. This brings us to our third. This is the last right-hand rule, though, so we should be good. I wrote a little bit here. For moving charges in magnetic fields, only the perpendicular component of the velocity results in a force. The resulting force on the charge is perpendicular to both the magnetic field and the charge's velocity. And this is the equation right here that you're going to want, right? So this is saying this is the magnetic force, and it's just equal to Q, whatever the charge is, times by V, whatever the velocity of the charge is, times by B, which is the strength of the magnetic field in Teslas. And then sine theta is there because it's only the component of the velocity that's perpendicular. So if you have the angle, and this is assuming this is the angle between the magnetic field and the velocity, right? Which if you go back here, right, to this little diagram here, right, I was giving you, because theta was relative to the magnetic field, right, you can see that there. So it's actually the sine of theta that you want, right? It's actually I didn't draw it here on this, but it's actually this, which would be the y component of the velocity that you want. So that's why that's there. But good to understand which actual component it is, because if you get a question where it's given to you a different way, you want to understand how to get which component of the velocity you want. So there's a simpler way to do this. We get a new right-hand rule. Point your right thumb in the direction of the velocity of the moving charged particle. Point your fingers. Well, maybe this here just shows it. I'll let you read that there. So this is your right hand. Point your thumb in the direction of the velocity of the particle. Point your fingers of your right hand in the direction of the magnetic field. And then, whichever direction your palm is facing, that's the direction of the force. Right? There are other variations of this. I also know some people do the right-hand rule with like more of a gun, if you will, where it's like they've got one finger sort of pointing out like that. And then their middle finger would sort of point that way, and then their thumb, I guess, hard to draw here, but that's their thumb sort of points up, and their other fingers are just curled in. It doesn't matter like how exactly you do it, but I kind of like find this one nice enough. And if you can do that, you can get the direction of it and it'll work. Okay. So let me look at an example. An alpha particle, I think we've seen these before, that's just a helium nucleus, 2 protons, 2 neutrons, is ejected from a radium nucleus with a velocity of 4 times 10 to the 6 meters per second at an angle of 60 degrees to a magnetic field of strength 0.5 Tesla. Determine the initial force on the particle and explain the motion of the particle as it moves through the magnetic field. Okay. Well, let me try to draw. I'll go this direction. Hopefully that works. So let's say this represents my magnetic field. And I think I can do this just on the page more or less. I've got this particle is moving, and it's got some velocity. Let's just say it's directly down. And this is 60 degrees. So this, again, I'm not trying to be three-dimensional with these two. I'm just saying let's just let the magnetic field be to the right, right? From left to right, it's just moving through here like this. Right, there's my magnetic field, and I've got a charged particle. It is a positive charge, so that works out well, because that's sort of what these right-hand rules are built for. If it was a negative charge, you'd actually have to use your left hand, or just go in the opposite direction. And so that means I want this this component of the velocity here doesn't do anything. It's parallel to the magnetic field, so it's actually this component here, which would be V sine 60, because I'm told that. This is actually what I want right here. This is the component of the velocity that is, I should indicate that here, that's perpendicular to the magnetic field. Right. I haven't actually worked out yet, so what is the charge on this, right? The charge on the alpha particle, well, it's just basically 2 protons. And the charge on a single proton is 1.602 times 10 to the negative 19 coulombs. So multiplying those, I get 3.204. And then if I consider the equation that I actually need to get the magnetic force on this thing, it equals Q V B sine theta, or I guess just QB V sine theta, since that's sort of the way I indicated it over there. And I'm given everything else, right? The charge I just worked out is 3.204 times 10 to the negative 19. The velocity I'm given is 4 times 10 to the 6 up at the top. And B was 0.5 Tesla, and then that's going to be times the sine of 60 degrees. And that's just a bunch of numbers. I can punch into a calculator, and that gives me 5.55 times by 10 to the negative 13 newtons. All right, so not a lot of force, but again, this is a very, very, very small particle, right? So that tiny bit of force could, cause some real acceleration if you consider the mass of an alpha particle is on the order of like 10 to the minus 27 kilograms, right? Acceleration could be pretty substantial. And that actually brings me to part B of this, right? Which asked about the direction of motion, right? So here we want to use the right-hand rule. And remember, we're really just considering the component of the velocity here that's perpendicular to the magnetic field. So, do you remember the right hand rule now for this one? All right. So, point your thumb of your right hand, right, and you can kind of like keep, like, you can almost start with like a completely open hand, right? You just sort of want like a hand like that, right? Just completely open, and really like the key here is this is like 90 degrees. In this case, though, it's got to point down, right? So I actually basically just drew that all wrong. You want your thumb to point in the direction here, and then you want your fingers to point in the direction of the magnetic field. So here's a nice right hand that might look just like that. And which way is my palm facing? If you try to lay your right hand on that, right, it's coming out of the page, right? So that's what we would say. We would say the particle would accelerate out of the page, since that's the direction the force is in, right? Um, Out of the